Welcome to today's paper reading. Today's paper is titled, A Comprehensive Survey of AI-Generated Content, AIGC, A History of Generative AI from Yihan to ChatGPT. This paper was published in the Journal of the ACM by Lichao and colleagues from Lehigh University, Carnegie Mellon University, and the University of Illinois at Chicago. The abstract highlights the growing attention on ChatGPT and other generative AI (GI) techniques. These techniques are part of Artificial Intelligence-Generated Content, AIGC, which focuses on creating digital content like images, music, and natural language using AI models. The primary goal of AIGC is to make content creation more efficient and accessible, producing high-quality content at a faster rate. This is achieved through the extraction and understanding of intent information from human instructions, and generating content based on this information and the model's knowledge. The abstract also notes the importance of large-scale models in AIGC, which improve intent extraction and generation results, leading to more realistic and high-quality content as the models grow in size and data. AI-generated content, AIGC, refers to content created using advanced generative AI techniques, which can automate the production of large amounts of content quickly. For instance, models like ChatGPT and DALL-E-2 are examples of AIGC. The process involves extracting intent from human instructions and generating content accordingly. Recent advancements in AIGC are due to more sophisticated models trained on larger datasets and the integration of new technologies, such as reinforcement learning from human feedback. Figure 1 showcases examples of AI-generated content, AIGC, in image generation. Specifically, text instructions are provided to the OpenAI DALL-E-2 model, which then generates 2 images based on these instructions. One notable example is the generation of an image depicting an astronaut riding a horse in a photorealistic style. This figure highlights the capabilities of AIGC models in creating unique and high-quality images from textual descriptions. Figure 2 provides an overview of AI-generated content, AIGC, categorizing generative AI, GI, models into unimodal and multimodal types. Unimodal models are designed to receive instructions from the same modality as the content they generate, such as text-to-text or image-to-image. In contrast, multimodal models can accept instructions from one modality and produce results in another, such as text-to-image or image-to-text. This distinction highlights the flexibility and capabilities of GI models in handling diverse content generation tasks. The history of generative AI begins with early models like hidden Markov models, HMMs, and Gaussian mixture models, GMMs, which were used to generate sequential data such as speech and time series. The advent of deep learning brought significant improvements, with the introduction of recurrent neural networks, RNNs, long short-term memory, LSTM, and gated recurrent units, GRUs, which allowed for better modeling of long dependencies. A major milestone was the introduction of generative adversarial networks, GNs, in 2014, which revolutionized image generation with impressive results across various applications. Figure 3 illustrates the historical evolution of generative AI across computer vision, CV, natural language processing, NLP, and vision language, VL, domains from 2014 to 2020. The timeline highlights significant milestones such as the introduction of StyleGN in CV, BERT, and GPT-3 in NLP, and the transformative impact of the transformer architecture across all domains. Key models like DALL-E and CLIP are also featured, showcasing the advancements and intersections of unimodal and multimodal AI generation techniques. The foundation models in AIGC are built upon the transformer architecture, which utilizes a self-attention mechanism to handle variable-length sequences. This architecture includes both an encoder and a decoder, with each layer consisting of multi-head attention and feed-forward neural networks. Pre-trained language models, such as BERT and GPT-3, leverage this architecture for tasks like masked language modeling and autoregressive language modeling. Additionally, reinforcement learning from human feedback, RLHF, is employed to fine-tune these models, ensuring their outputs align better with human preferences. This process involves pre-training a model, training a reward model, and fine-tuning with reinforcement learning using algorithms like proximal policy optimization, PPO. Figure 4 categorizes pre-trained large language models, LLMs, based on their information flow and training objectives. The black line indicates bidirectional information flow, typical in encoder models like BERT, which are trained with context-aware objectives. The gray line represents left-to-right information flow, characteristic of decoder models such as GPT, trained with autoregressive objectives. Encoder-decoder models, exemplified by T5 and BART, integrate both approaches, using context-aware structures for encoding and left-to-right structures for decoding, thereby enhancing performance across various tasks. Figure 5 presents statistics on the size of various models and their training speeds across different computing devices. The model size is shown to range from 100 million to 100 billion parameters, highlighting the significant scale of modern AI models. Training speed is measured based on devices such as the V100, A100, and RTX 8000, illustrating the performance differences in hardware. Key models featured include GPT, BERT, T5, GPT-3, Megatron, and Roberta, each representing a milestone in the evolution of AI-generated content. This figure underscores the rapid advancements in both model complexity and computational efficiency, driving the progress of AI technologies. This section introduces state-of-the-art unimodal generative models. Generative language models like GPT-3, BART, and T5 are discussed, which are used for tasks such as dialogue systems, translation, and question answering. These models leverage pre-trained architectures including encoders and decoders. Additionally, generative vision models such as GNs, VEs, and normalizing flows are covered, focusing on their applications in image generation, training stability, and output quality. Notable models include progressive GN and style GN. The section also touches on multimodal models, which integrate vision and language, exemplified by models like CLIP, DALL-E-2, and IMAGIN, which use an encoder-decoder architecture to generate content across different modalities. Figure 10 illustrates two types of to-language decoder models, jointly trained models and frozen models. Jointly trained models are typically trained end-to-end, ensuring that both the image encoder and language decoder are optimized together. In contrast, frozen models maintain the language decoder in a frozen state, meaning it is not updated during training. Instead, only the image encoder is trained, which can be seen as a form of multimodal prompting. This approach leverages the success of prompting and in-context learning in NLP, raising questions about its effectiveness in multimodal settings. The figure highlights the differences in training strategies and their implications for model performance in vision-language tasks. Figure 11 provides a detailed look at the model structure of DALL-E-2. The diagram is divided into two main sections, the CLIP pre-training process above the dotted line and the image generation process below it. The CLIP pre-training process is crucial for aligning the vision and language modalities, ensuring that the model can effectively interpret and generate images based on textual instructions. The image generation process begins with a text encoder that takes an instruction and converts it into a representation. This representation is then processed by a prior network and a diffusion model, which work together to decode the representation and produce the final output image. This structure highlights the integration of advanced techniques in both pre-training and image generation to achieve high-quality results. Figure 12 presents DALL-E, a KG-to-text generation model designed to bridge the structural gap between knowledge graphs, KG, and graphs through dual encoding. The model employs a GCN-based graph encoder to extract structural information from the input graph. Additionally, a neural planner is utilized to create a sequential content plan, which is essential for generating linear output text. This dual encoding approach ensures that both the structural and sequential aspects of the graph are effectively captured and translated into coherent text. Figure 13 presents MOMU, a cross-modal text molecule generation model. MOMU addresses the challenge of generating molecule graphs from text descriptions by employing a graph-based multimodal framework. This framework trains two separate encoders jointly through contrastive learning to align the semantic spaces of text and molecules, even with weakly paired cross-modal data. MoMA's design allows it to be adaptable to various downstream tasks beyond de novo molecule graph generation, showcasing its versatility and effectiveness in cross-modal data processing. Figure 6 illustrates the architecture of InstructGPT, detailing the process of fine-tuning GPT-3. Initially, demonstration data is gathered with human labelers, which is then utilized to fine-tune GPT-3. Subsequently, prompts and their corresponding answers are sampled from the language model, and human labelers rank these answers from best to worst. This ranked data is employed to train a reward model. Finally, with the trained reward model, the language model can be optimized according to the preferences of human labelers. Figure 7 categorizes vision generative models into several key types. First, generative adversarial networks, GNs, consist of a generator and a discriminator, where the generator learns to create new data resembling real examples, and the discriminator evaluates the authenticity of the generated data. Second, variational autoencoders, VAEs, aim to map data to a probabilistic distribution and learn a reconstruction close to the original input. Lastly, diffusion models progressively corrupt data with multiple level noise perturbations and then learn to reverse this process for sample generation. Each category has its unique approach to generating realistic and diverse visual content. Figure 8 illustrates the general structure of generative vision language models, which is divided into an encoder part and a decoder part. The encoder's role is to transform the input data into a latent representation, capturing essential features. Subsequently, the decoder processes this latent representation to produce the final output, ensuring the generated content aligns with the input's semantic context. This encoder-decoder framework is fundamental in multimodal generation tasks, facilitating the seamless integration and interaction between different modalities. Figure 9 illustrates the two primary types of vision language encoders: concatenated encoders and cross-aligned encoders. Concatenated encoders process concatenated embeddings from various raw modalities, while cross-aligned encoders employ a two-tower structure to align in abstract modalities. Both encoder types utilize pre-training tasks to enhance the alignment of multimodal representations. In the domain of chatbots, notable examples include Xiaoice developed by Microsoft, Mina by Google, and ChatGPT by OpenAI. For art generation, significant advancements have been made by OpenAI's DALL-E series, Stability.AI's Dream Studio, and Google's Imagen. In music generation, AIVA by IVA Technologies and OpenAI's Jukebox have made significant strides, along with the use of symbolic representations for music creation. Figure 14 presents a comprehensive relation graph that visually maps out the current landscape of research areas, applications, and related companies. The graph uses different colored circles to categorize these elements. Dark blue circles signify various research areas, light blue circles denote specific applications, and green circles represent companies involved in these fields. This visual representation helps in understanding the interconnectedness and the dynamic relationship between research, application development, and corporate involvement in the domain. Table 1 provides a comprehensive overview of the applications of generative AI models across various research areas, applications, and related companies. The table categorizes these elements using different colored circles: dark blue for research areas, light blue for applications, and green for companies. This visual representation helps in understanding the relationship and distribution of generative AI models in different sectors. The table also lists specific examples of applications and the corresponding companies that have developed these models, along with the years they were introduced and relevant paper links. This structure aids in identifying the evolution and current state of generative AI applications. Efficiency in AI-generated content, AIGC, is a critical challenge, particularly in the context of deep generative AI models. Inference efficiency focuses on the practical deployment of models, considering factors such as model size, speed, and resource consumption during inference. Training efficiency, on the other hand, addresses the speed and resource requirements of training models, including scalability and data needs. Prompt learning is a recent approach that aims to enhance efficiency by using templates to guide pre-trained models, enabling them to adapt to new tasks without extensive retraining. Figure 15 illustrates the general procedure of prompt learning applied to emotion detection tasks. Initially, the user must craft a prompt that accurately reflects the problem at hand. To enhance performance, the user can incorporate in-context learning and chain-of-thought (COT) techniques. Subsequently, a large language model (LLM) generates appropriate words to fill in the blanks within the prompt. The final step involves a verbalizer, which maps the generated word to a specific emotion classification category. The security of AI-generated content, AIGC, is a significant concern, particularly regarding factuality. Models like ChatGPT can produce unreliable, or even absurd answers, which can spread misinformation. NewsGuard studies show that AI tools are being used to disseminate false information on a large scale. Additionally, AIGC must be non-toxic and unbiased. OpenAI's InstructGPT and Google's Lambda are examples of models designed to mitigate these issues by aligning with human preferences and ensuring safe responses. Privacy is another critical area of concern. Membership inference attacks and data extraction threats highlight the vulnerabilities in AIGC models. These attacks exploit the memorization properties of large models, potentially leaking sensitive information. Addressing these security and privacy concerns is essential for the responsible use of AIGC. In high-stakes applications, AIGC faces challenges in ensuring accuracy, reliability, and transparency. These domains require near-zero fault tolerance, as seen in the case of Galactica. Specialization and generalization in AIGC hinge on the choice of foundation models and the balance between diverse and specialized datasets. Continual learning and retraining strategies are essential for keeping models updated with new information, yet understanding when to apply each remains a key challenge. Reasoning in AIGC is crucial for tasks requiring logical inference. Techniques like chain-of-thought prompting aim to enhance model reasoning capabilities. Scaling up models involves significant resource constraints and requires careful hyperparameter design. Social issues in AIGC include concerns about bias, ethics, and the impact on society, necessitating responsible development and deployment. This survey offers a thorough review of the history and recent progress in AIGC, emphasizing both unimodal and multimodal generative models. It also covers the applications of generative AI, the techniques commonly used in AIGC, and the issues related to trustworthiness and responsibility. The survey identifies open problems and future directions for AIGC, suggesting potential areas for innovation and development. The primary goal is to provide readers with a comprehensive understanding of recent advancements and future challenges in generative AI. The analysis of the general framework of AI generation aims to differentiate contemporary models from their predecessors. The survey hopes to deepen readers' insights into this field and will continue to explore this topic for more comprehensive analysis. Thank you for watching.